Hi everyone, welcome to INF10004 Database Analysis and Design Lecture 10. Now in today we are going to learn four topics: network diagrams, recursive relationships, indexes and normalization. So let's first work on network diagram. A network diagram is a visual method of showing the relationships, entities and the foreign keys based on your relational schema, right? So once you have done your entity relationship diagram, sometimes it looks a bit messy, right? So there are lots of entities, lots of relationships, lots of attributes. So sometimes it won't make any sense if you see a kind of a messy big diagram. So network diagram is another diagram that we can use with the entity relationship diagram to show just the foreign keys and the entities and how these entities are related to each other with which foreign key. So basically in a network diagram we are showing three things: entities, we are represented by in rectangles as we did in entity relationship diagrams, and then we are showing the relationships. We show the relationship by using arrows connecting to each entity or relation, and then we are showing only the foreign keys, right? So foreign keys, um, we have to choose what foreign keys of each entity relation or entity consist of, and we attach that foreign key to each relation. Now when you're drawing the network diagram, you need to remember that arrows are always pointing from the foreign key to the primary key, right? It's pointing from the foreign key to the primary key. So as a rule of thumb, normally we draw the network diagram with the weakest entity, right? So we use the bottom up approach. So weakest table basically comes at the bottom. Alright, let's work on a small example, a network diagram for a relational model. Now think about this small relational schema. So in this case we have three entities: student, subject and the enrollment. So student entity consists of student number, surname, first name and the address. So student number is the primary key. The subject entity consists of subject code, title and the credit points, and subject code is the primary key. And think about the enrollment entity. So enrollment entity consists of student number, subject code, year, semester and the grade. So it looks like enrollment entity is the weak entity. So it has a composite identifier. So the composite identifier here is student number, subject code, year and the semester. So that means enrollment entity borrows student number from the student table, subject code from the subject table, and it has its own two attributes, year and semester. So that means student number and subject code are the foreign keys. So how are you going to show this in a network diagram? So as I mentioned before, in a network diagram we need to show the relations. So relations we show as a boxes, like what we did in entity relationship diagram. So we have student entity, we have subject entity and we have the enrollment entity, and then we are showing the relationships. Relationship shows by the arrow keys or arrows, right? So these arrows actually shows which foreign keys are related with which primary keys. So basically, enrollment borrows the student number from the student entity and subject code from the subject entity. So the foreign key of the enrollment entity pointing towards the primary key of the student, and the foreign key of the enrollment entity again pointing towards the primary key of the subject. So this is basically means the network diagram. Now remember, in a network diagram we are not going to show any attributes. We are showing only the foreign keys. So why we use the network diagram? Because if we use the network diagram with the entity relationship diagram, software developers or database developer can identify the connection very clearly rather than going through each and every attribute. Recursive relationships. Now this is a very small topic. So we are showing another type of relationship between the entities and the attributes itself. So the recursive relationship is a single relationship between two instances of the same entity type. Now let's go through an example. Now think about this small example. Think about we have bunch of business rules. Now these business rules with respect to this particular organization says every employee has an employee number. An employee may have a manager. A manager may manage many employees. A manager is an employee as well. So they are basically talking about employee entity. And each employee has employee numbers. And managers managing employees and managers also has an employee number. That is what we mean by this. So how are you going to show this relationship in an entity relationship diagram? So this is how we are showing that relationship. Now as I mentioned before, a recursive relationship is a relationship between instances of a single entity type. So do we have a recursive relationship here? Now let's go through this schema. An employee may be managed by one employee or one manager. A manager may manage many employees. So we have employees, employee number is the primary key, and we have other attributes. So one employee or one employee manages many employees, isn't it? And one manager can, or one employee can manage only one employee. So that is what do you mean by this relationship. So there is a one-to-many relationship between the instances of the same entity, because the manager also an employee. So the next question is how we are going to show that in our create table statement. So let's do some sort of an example. Now think about this employee table. So we have employee numbers, we have names, we have salaries, and we have manager numbers. So why we put the manager number here? Because you can see we have the many end ended up in the same entity. Now as you know the rule, if the many end attached to an entity, that means the foreign key goes there. So what is this foreign key? This foreign key is the primary key of the related entity. So what is the primary key of the related entity? Is the employee number. So this employee number pointing to say another employee number in the same entity. So that means we need to have an additional column, but the problem is we can't name it as the same name. So we need to give another a name for that particular foreign key column. So in this case, we use another name called manager name. Right. So we have a bunch of questions here. Which employee is a Jane Pitt's manager? So Jane Pitt is employee number 119. Jane Pitt manages by manager number 299. So number 299 is Sue Smith. The Sue Smith has another manager, number 400. Number 400 is Claire Jones. And Claire Jones' manager number is now. In other words, the foreign key is now. So what do you mean by this? So Claire Jones probably is on the top of the hierarchy in the organization. She doesn't have any manager at all. So as a rule, you can see the foreign keys can be now. Right. So how are you going to implement this in the Oracle environment? Now remember, a foreign key column may reference a primary key value in the same table. The example that we have talked, that's called the recursive relationship. The question is, we can't have the same name. We can't have the same primary key name as our foreign key name. So we need to give a different name in this case. Now remember, when you link the foreign keys and primary keys, it's not the names that link by the Oracle. It's linking the values associated in the names. So the values associated in employee number links with the value associated in the manager number. So in this case, I can have now create table statement. So create table employee, employee name, employee number, salary, and my foreign key now manager number. So the foreign key manager number references to the employee. So it comes back again to the same table. Now the question is, now since we have the same table, if you run SQL queries in order to select some rows, we have a problem because SQL select statements cannot access two rows from the same table at the same time. So in order to avoid that, we need to create another, not to create another table, but we need to trick the Oracle to believe that there are two tables. So that means we can give second table another alias. In this case, I use MGR table. So I use employee table as EMP table, and another copy of employee table I refer to it as MGR table. So in that case, I have two copies. So one copy, the first copy is pointing its foreign keys to the primary key of the second copy. So this is how we implement it in a select statement. So in this select statement, we have a join or inner join with two logical tables using primary key and the foreign key. So here I am selecting the employee names and the manager names. So I need a kind of a report something like this, all the employee names and all the managers who managing these employees. So I can run a select statement something like this. Select name. This name is coming from the employee table. So emp dot name, and the second name coming from my manager table, the second copy, mgr dot name. From employee emp and inner join employee manager, and then we give the condition employee manager number is equal to manager employee number. So this is the first copy, primary key, and this is the second copy, foreign key. So basically now if you run this statement, this one, inner join, we have a problem now, because what is the problem of the inner join? The problem of the inner join is it actually ignores the null values, isn't it? So in order to avoid that, because if we need to select all the employee irrespective of the manager numbers or manager names, even the Claire Jones and Dave Bly need to be there. So inner join will not going to work in this particular situation because we have nulls. So in order to avoid that, we can use left outer join or right outer join. So in this case, I'm using the left outer join. Same query, I replace it with the left outer join. So in the left outer join means my left table data will display irrespective of the null values. So my left table is the employee table, that is the first table. So I need to have all the employee names irrespective of whether they have null foreign keys, right? So this is my left table, and manager is my right table. So if I use the left outer join, my left table has to be the employee table. So my output now looks like this. So I have now Claire Jones, I have now Dave Bly, and then there is no managers associated with Claire Jones and the Dave Bly. So outer join shows all the employees rows, even foreign key does not match with the primary key. Physical storage and access methods. Now when it comes to relational database management system, it's very important to design these systems to retrieve data fast as possible. So we record data in databases using different tables with the relationships. So we need to have a mechanism to retrieve this data as soon as possible. So data retrieval is one of the key aspects of relational database management systems. Now when it comes to data retrieval, there are different alternatives are available in database management systems. Now in this topic, we are going to cover the basics. Now think about an example. How do you going to find a specific song in a compact disc? Either you can type the song number, or you can rewind or fast forward the track and find the specific song you requested. How about the videotape? How are you going to find out a specific episode or a song in a videotape? Definitely it's not you can't type the track number or the position number. you need to rewind it, you need to fast forward it until you find the specific position of what you are seeking. Now think about a book. How are you going to find the information in a book? There are some specific ways that you can use to find information on a book. The first method is you can either sequentially read from page 1 until you end up with getting the required information. The second method is we can refer to the table of contents and the subheadings, and then we can find out the required page or pages what we are looking at. The third method is we can use an index. Now when you have your book, you can see that the books, the last pages of the book probably contain the indexes. So it contains the major topics and it contains the page number that these topics that we can referring to. So this subject we are not going to discuss sophisticated data storage mechanisms or data retrieval mechanism. There are other subjects or units that offered in higher education which talk about these kind of things. But in coming couple of slides, we are actually discussing very simplified way of to retrieve the data from the database management systems. Now think about this example. Now assume that we have a table called employee table. It has 100 rows. That means we have 100 employees in our employee table. Employee number is the primary key and the employee number is 3 digits in length. So employees are stored in the employee table in a random order. So employee number is the primary key. Now our task is to find the details about the employee number 83. So what are the alternatives we have to find the employee number 83? So the alternative number 1 is we can sequentially read each and every row until we find the employee number 83. So we read each row by row by beginning of the table until the required row is found. Now typically in database management systems or databases, in order to evaluate 100 separate rows, it need to actually read 100 times. Now think about each row. Each row may contain lots of information because each row refers to many values in each and every column. So reading and writing, right, or inputs or output into the memory is the slowest part in a computer, right? So we call it as disk I/O. So that is the slowest compute activity. It consumes lots of resources. So basically, if you want to read 100 records nowadays, probably it need to actually on average search for employee table 50 times. Or in other words, it need to read 50 records because the reason is in reality database management systems will read rows as blocks of data. For example, it read 2 kilobytes of data into the memory and through the memory it will search the required record. So therefore the number of rows it can be read into memory on average will take into account 50. So that is the slowest part. The second alternative is we can use indexes. So what do you mean by the index? It's exactly the same way that we have the index in the books. So the index is a mechanism that we can use to speed up the access to data. It's similar to the catalog in the library. So how are we going to search a book in the library? We can either search it, the book by the author, or title, or the subject. Or sometimes we can use the index of the book. Right. Right. Now, when it comes to database management system, there are so many sophisticated indexes are available. We are not going to cover these indexes, but there are few types of indexes are there. So we have B trees, we have clusters, hash indexes, join, bitmap, and even some indexing methods determine the physical location or the sequence of rows in the disk. Alright, now let's think about how we're going to build an index. How the database management system going to build an index based on the table. Now, usually database management systems keep an index based on the primary key value. Now think about you are trying to create a table in your database. You are trying to create a table called employee table which contains 4 columns: employee number, first name, surname, and the department. So when you run create table statement and when you specify a primary key column in your create table statement, as soon as you run this create table statement, the database management system automatically creates an index based on the primary key. So that index has only 2 columns: the primary key column or the key column and the address of that key column. So in this example, I use the address or the disk address as the row number to simplify our discussion. Now we are trying to insert the first row to our table. So we are inserting the row number or employee number 109. So we are running insert into command and press enter. Then what happens once you press enter, the row will add it to your table, employee table. It will record the address of that particular employee number, and then it will insert a record to your index table. So it inserting the primary key value and the address of the primary key value. So when you try to insert the second row, in this example we are trying to insert the employee number 13. So we run insert into command and then press enter. So what will happen? It will insert the second row to my employee table. It will record the address number, in this case the row number, and then it will insert a record into the index file as well. Now what happens when it insert the index file? It will then get it sorted according to the key or the primary key value. So now employee number 13 jumps first and employee number 109 stays as second. Now we are trying to insert the third row to our employee table. In this time, the employee number 27. So we run the insert into command and press enter. A row is inserted into the employee table. and the row is basically added to the end of the table, isn't it? And then it records the address, and then it will insert a row or the primary key, or we call it as actually a search key, to the index file, and it will automatically sorted according to key value. Now number 13 jumps first, number 27 comes second, and number 109 comes third. And then the row numbers adjust accordingly, or the address adjust accordingly. So likewise, think about, we are inserting all the rows into our employee table, and then database management system will create an index table based on the primary key value or the search key value, and it will record the row numbers. Now remember, users can't access the index file. Users can access their own files, but users can't access. So these index files basically maintained by the database management system in a machine readable form. It's not human readable form. So obviously, you can see if you compare these two tables, first table is my index table, the second table is my original table. So obviously, the index table, or in this case the primary key index table, is much smaller than the table that we have created. So that means if you try to search something, the searching of index file is much more quicker than searching of your original file. And the other advantage is the index file always maintains according to the sequence of the key or sequence of the primary key. So this makes searching quicker. So how are we going to find, if I want to find employee number 289. So if I run a statement, select employee name, address, and other information from the employee where the employee number is 289. So how we going to execute in database management systems? So database management system, as I mentioned before, use many types of search methods. So let's use a very basic search method called the binary search method. Now in the binary search method, what happens, DBMS or database management systems try to load the index first into the memory and split the index into half. So that is what we mean by the binary. It split the index into half, and it will take the middle position. Now it will take the middle position of the index. Now once it goes to the middle position, or the split into the half, and we take the middle position, then it will see whether the key that we are searching, now the key in this case is employee number 289, whether it's located in the upper half or the lower half of this index. So obviously it located in the lower half. So that means DBMS now can ignore the top part. The half of the index now has gone. We don't need to actually search the upper half. Then it comes to the second part, right? So it already eliminated half of the index, and then again it split into two, and it will take the middle position. and then see whether the key that we are searching 289 is located upper portion or it is located in the lower portion. So in this case it located in the lower portion. So that means again I need not to read the upper portion of the index. So I can ignore the upper portion. And then it takes only the lower portion of the index. And again it splits into two. Now number 289, once it goes to this location, number 289 is the key that we are looking at. So the key is located in the lowest portion. So what will happen once it recorded or once it located the number 289, that is what we are looking at, and it will search the original table to find out the address of that located key. So address of the located key is the row number 11. Then it will read the whole row into the memory. Advantages of using indexes. Now one of the key advantage of using index is actually it's a quick method to locate a particular row or rows. So that is the main advantage. And also large portion of index can be read into the computer memory at once, right? So basically then it actually fasters how you access the record, isn't it? So that will lower the number of read and write or inputs and outputs the disks, because once your index has been loaded to compute memory, it's slicing and dicing and dividing the indexes into and doing the binary search all happens inside the memory. So the computer need not to read back from the disk. So it basically speeds up the record retrieval time. Now it says as an example to find this employee number 289. On average we actually need to have only two reads, isn't it? The first read is we need to read the index into our memory, computer memory, and the slicing and dicing and binary search is going on inside the memory. And the second read is once the record has been located, the second read is the reading that particular row from the address of that index. So basically we have only two or couple of reads in order to locate a particular record or the row in a given database. Now we actually learn only the one search method, that is called the binary search method. That is the one basic search method available to almost every database management systems. As I mentioned before, there are more complex indexing options available in database management systems. And one of the key important thing that you need to remember is it is not possible us to read or display the contents of an index. It's recorded in the machine readable form, or in other words it's recorded in the binary format, or it may be compressed in order to reduce the size of the index. So humans can't read it or humans can't access it. And then the other important thing is when it comes to the databases or database management system, you can have multiple options or methods that your indexes or tables can be set up. right? Now how are we going to create an index? Can we create our own index for tables? Yes, we can. So it's relatively very easy to create an index, right? So this is the syntax: create index, and we can give a name of the index, and on is a keyword. We need to specify the table name, and we need to specify the column name. So this will create an index which stores the surname in a kind of a sorted sequence. Now when you create the indexes by yourself, that index can have duplicate values. That's perfectly okay. For example, in this case, surname is not the primary key. So there can be many similar surnames in your file. But sometimes you may think, how can we eliminate the duplicate? How can we restrict the duplicates? Most of the DBMS has an option where we can actually uh, limit the duplicates, so we can get rid of duplicates, right? So that setup can be done. It can be done actually not normal users, but it has to be done through system users, right? So system users has the access how to set up this option. Right, now think about this example. In this case, earlier we have created an index based on the surname. Now if you think about this example, this is an index created based on the above this particular index, right? So we have surnames, we have uh, address or record number, address of the disk, and you can see there are lots of duplicate values. Now if I run a statement like this, select asterisk from employee where surname is equal to Taylor, how can we search the specified uh, output based on this query? Right, so in this particular instance, still we computer or the application or the BMS will do the binary search. It divide the index into half, and then the matching value or the tail sits in the lower half, so it will ignore the upper half, and again it will divide the lower half into two, and then it definitely the tail will in the lower half, and then once it locates the first tailor, and then it will kind of do another search in the index, the upper record and the lower record, to see whether there is another tailor is there. If another tailor is there, it will go on like that, right? And then try to locate the specified index which it belongs to, and then read that particular record from the disk and display as a result set. So subsequently what will happen, it will read one or two reads from the disks. So what are the cost of creating indexes? Can we create as many indexes as possible? Since we can create indexes, so what are the costs and what are the advantages? Let's think about the advantages first. So indexes basically speed up the data retrieval times. The other question is, why can't we create an index for each and every column? Because if you have 5 columns in your table, why can't we create an index? So we know how to create index. So why can't we create indexes in each and every column? Um, to maintain an index is a tedious process, right? Uh, it actually consumes some disk space, but at nowadays disk space is not a major factor, but if you think about the table with billions of trillions of rows, actually it makes sense, right? Disk space makes sense. And the other important thing, disadvantage, is update time. Now what happens each time when you do some modification or update or inserting any record into your original table, you need to subsequently update your index and sort it out according to the key value, right? So it takes little time. So if you create more and more indexes for a table, that means there are too many tables need to be updated each time if the value has been changed in a specified row, right? So that is one of the major disadvantage. So it creates an unacceptable delays. Now the next question is, how often we are using these indexes? Are all indexes needed? Now if we need an indexes, for example, sometimes in practice in industry we usually create indexes if you want to run some reports, right? For example, once a month or weekly we need to run a report which requires to integrate data from 10, 15 or 30 or 40 tables, right? uh, for because when to run the report so quickly or produce the report so quickly, we need to have indexes, so it will speed up our report generating activity, isn't it? So what we can do is we can create an index and we can run the reports and then we can drop the indexes. So generate the index, run the reports and drop the indexes. Nowadays database management systems actually very intelligent. They have functionality called optimizers, right? So optimizers can determine when to use index and when not to use the indexes, right? So when you install a database management system, database administrators can actually program it when to use indexes, right? If you have small number of rows or small number of rows in a particular table, but basically we don't need any indexes, right? Or we can create in a small index based on the primary key, right? So it is the quickest method to retrieve information from that particular small table, right? But even if you create an index database management system, because they have optimizers, it will determine whether to use that index or not. Because if you use that index for a small table, for example, if you have only 100 records, it still reduces the retrieval time because we need to update the index before we retrieve anything, right? So optimizers will determine, okay, do we need still require index, or is it better to load the entire table into the memory and do a quick search and then locate the file or locate the record that it requires. Okay, so optimizers probably attempt to reduce the time taken to process a query. There are some instances that we need to have multi-level indexes, index with index. Now if you think about this small example, we have a table and we have an index. At this time we have an index split into segments, right? Segment 1, segment 2, segment 3, and each segment contains specified number of keys. So and then we have another index based on the first index. So that index actually keep the record of the index number, sorry, the segment number, and the last key of each segment. So the segment number 1 or address of segment 1, the last key is 56. Address of segment 2, the last key is 112. Segment of 3, last key is 215, so on and so forth. So if you have billions of trillions of rows tables, probably database management systems will create index of indexes. Okay. So how can we search a record if you have index of indexes? So it do the binary search. Again, if I want to locate, say for example, employee number 109. So what will happen? It will roll the first index. Then it will first see employee number 109 belongs to which segment. So you know the second index I have keep the last record, isn't it? So actually it will first load the second small index first, and it will determine employee number 101 located in which segment. So not in the first one, because this is the last record. It definitely belongs to the second segment because the last record of that segment is 112. So 109 is inside this. Then it will jump to segment 2 and then do the binary search, splitting and dicing. And then it will record the 109. The address of 109 is row number 17, and then it will read the employee file and locate the row number 17. So this is how it works in a multi-level index environment. Database normalization. Now this is a new topic. Now normalization is a database design technique like entity relationship diagrams that we use. So we have diagrammatic technique that we can use to design databases, and normalization is another technique that we can generate a relational schema. So it is an alternative way of creating the databases. Okay, so in normalization we don't use any diagrams. So in a normalization there are so many there are few steps that we need to undertake. The aim of the normalization is to achieve basically third normal form, right? So there are so many normalization steps currently in, but 99.9 business cases or business design of databases can be achieved through the third normal form. Now there are stages of normalization. So before we go into that stages, why we need normalization? What do you mean by the unnormalized data? In unnormalized database, you know that the tables can have potential anomalies, right? If you have unnormalized data, so we may have insert anomalies, update anomalies, deletion anomalies. By creating normalized database, we actually trying to eliminate these anomalies, right? So each stage in the normalization process, we are actually eliminating some of these anomalies. Okay. Now these are the stages in normalization. So our ultimate objective is to achieve third normal form. We called it as 3NF, right? Right, now let's go through these steps. Now, unnormalized data means you have lots of redundant information, isn't it? So from the unnormalized data to achieve the first normalized data base or 1NF, what we need to do is we need to remove so-called repeating groups. From first normal form to second normal form, we need to do some stuff. We need to remove part key dependencies. In order to achieve third normal form, from the second normal form, we need to remove non-key dependencies. So if you remove these stuff, removing repeating groups, removing part key dependencies, removing non-key dependencies, you can achieve the third normal form. There are so many other stages in the normalizations, like boys code normal form, fourth normal form, fifth normal form, but we are not going to cover in this unit, right? So as I mentioned before, 99% of business problems can be achieved or can be eliminated by going through these three normal forms. Alright, let's go through an example. This is an example of a normalized data table. Right, so in this table we have, now can go through that. So we have student IDs, student names, major, right, subject code, subject titles, convener, convener location, and grades. It looks like there are lots of information combined in this particular table. It looks like a small spreadsheet, right? So now we usually call these sort of tables as zero normal form table because it's in the unnormalized format. Now our first task is to remove the repeating entities. Or in other words, in order to achieve first normal form from the zero normal form, we need to remove the repeating entities. So what do you mean by the repeating entity? Now you can see each cell in the normalized database must contain only one value. But in this case, the column number 4 contains two values in one cell. And column number 5 contains two values in one cell. Likewise, the rest of the columns also contain two values. So how can we eliminate these values? By splitting this into two records, isn't it? Because it looks like they have combined two rows into one. So if you repeat the other stuff here, like information systems, bright, and student ID, here we can actually create another separate row. So that is what do you mean by eliminate the repeating entities. So if you eliminate the repeating entities, your final table now looks like this. So each cell now contains single value, right? So now we achieve the first normal form. So in order to achieve the second normal form, we need to find out first, as a first step, what is the primary key of this particular table. So we call that primary key as the universal key or universal relation key or universal relation key. Yeah. So this is called the universal relation because it combines few information, right? So in that universal relation or universal table, we have universal key. So what is the universal key or the primary key of this particular entity? Now that is the most hardest part. If you have a spreadsheet like a table, finding a prime, now this is a Mickey Mouse table, right? But imagine you have a table with 30 to 40 columns with different values. So what we need to do is to come up with a primary key or the universal key for this particular table. What do you think? So what should be the primary key of this particular universal entity? Is it a student ID or is it something else? Is it student ID combines with some other columns? So identifying the primary key in a given table is a bit challenging. So one of the rule that you need to keep in mind is a primary key should contain the fewest columns as possible. Fewest columns as possible. So how many columns do you think that we can combine in order to make a primary key? So we can combine the student ID column and the subject code column. So that will give you a unique identifier for each and every row. So we need to remember we need to create fewest possible columns. Another person may take a convener name or subject title added to this universal key, but then again it's wrong because student ID and subject code will determine the uniqueness of this particular table, because we don't need more and more extra in, columns. The second step is, now we need to think, once you determine the universal key, we need to think about functional dependencies. Now remember in last lecture we have talked about functional dependencies. Functional dependencies, columns, some attributes depends on the primary key, isn't it? For example, if you think about this example, student ID and subject code, some values or some columns depends on the student ID and some columns are depends on the subject code. So we can say something like this: student ID determines the student name, right? So there is only one student name to that particular student ID. So is there only one student name for that particular student ID? Yes. If it is yes, then there is a functional dependency, right? Right. So we know the universal key now. We know what do you mean by the functional dependency. But there is one more thing that we need to know in order to achieve the second normal form. So we need to determine the part key dependencies. A part key dependency is where a particular column in our universal table dependent on the part of the universal key. So how many parts we have in this universal primary key? Two parts, student ID and the subject code. And some of the columns or attributes in the universal relation depends on the student ID, and some of the attributes dependent on the subject code. So we need to now determine what are the partial key dependencies. Which column determines student ID, which columns determined by the subject code. So if So once you establish that, now we have the student name is dependent on student ID, right? And what else? Yeah, basically student name, right? Dependent on student ID. So what we can do, if we have the partial key dependencies or part key dependencies, take that columns out from your universal relation and put it into another relation. In this case, I have created another relation or the table called student. So I put the student ID, the part key, and then I grab that column and then shift that column to this particular entity, student entity. What else determined by the student ID? Again, the course that they have enrolled in, each student enrolled in, determined by the student ID. So I can take the course name or course and then take this out from the universal relation, and then I can put that into the newly created entity. So what we have actually done here, we basically created a strong entity. So what is this relation? The universal relation, what is actually this universal relation looks like? What kind of entity is this? This is a very big weak entity, right? So that means from this big weak entity in the second normal, at the second normal form, we are creating a strong entity. What you have done in entity relationship diagram, how you have, what is the first step? First step is we first create strong entities and then we identify weak entities, isn't it? But in this case, we first identify the universal relation that is more, the biggest weak entity, and then we create the strong entity, other way around. So completely other way around. So this is what we have done here. So we take the student ID, the part key, and all the dependents into another entity called student relation, right? So student ID is a part of this universal key. Right, now we need to do the same process for our second key, subject code. So which columns, the rest of this determined by the subject code. Subject title, yep, convener name basically, and also maybe perhaps convener location. So subject title, convener name, convener location depends on the subject code. So that means we can write something like this. Subject code determine the subject title, subject code determine the convener name, and subject code determine the convener location. So then, as we did earlier, we need to move the part key dependencies to a new table. So this is the table, then we need to determine, now this is my primary key of that table. So we have created another strong entity. So this is what we have done. First we have created the student strong entity. Now we have created the subject strong entity. So now what happened to the universal relation? It has shrinked. So that means now we have achieved the second normal form. So the next second normal form means once you eliminate the part key dependencies, you are now in second normal form. Now the third step is to achieve third normal form. To achieve the third normal form, this is the process we need to go through. We need to find out what are the non-key dependencies. So non-key dependencies is where a particular column has a dependency on another column. So that column is not the part of the universal key or the primary key. So what are the columns in our tables dependent on the other columns which is not part of the primary key? Now if you go through the subject entity, you can see the convener locations. So convener location or the convener name, in other words, actually determined by dependent on the location, that the office location. Or in other words, let's put the other way around. Convener location determined by the convener name. So if you know the convener name, we can identify which location he or she belongs to. So that means we can open another entity called convener, and then I can take that convener location from that table and put that here and duplicate the convener name. Now we have removed the part key dependency. Do we have any other part key dependencies? No. So this is what we have done. We take the convener location and put it into another table, right? And then we linked it with the convener name. So this is a part key, right? So basically what we have done, we first created a universal relation by eliminating the repeating groups, right? So this is what we have done first, and then we remove the part key dependencies based on the two parts of the key, subject code and student ID. So we grab the sum of the information which belongs to a student ID to the sum another unit called student, and then we created another part key dependency table called subject code. Yeah, this subject table, and then finally we remove the part non-key dependency and created a table which reflect the non-keys, right? So basically now we have achieved our all these tables that we required. So we have now what is the universal relation in this case? This is the universal relation. So in the universal relation we have ended up student ID, subject code and the grade only, and it is pointing the student ID to the student table. It's a strong entity, and it is pointing the subject code to the subject table. It's a strong entity, and then by eliminating non-key dependencies we created another entity called convener. So this universal relation now stringed, and it looks like this is an enrollment entity. So weak enrollment entity. So we have uh, three strong entities and one weak entity. So what are the steps to achieve third normal form? We need to start with our universal relation. So universal relation is that the one large table or the large table that looks like an Excel spreadsheet, right? Step one is first we need to eliminate all the repeating entities or repeating groups by ensuring every cell has a value, right? Each cell must contain only one single value. So if you eliminate that, we are now in first normal form. Step 2 is we need to identify the universal key or the primary key for that universal entity or the table. Okay. Step 3 is we need to remove the part key dependencies. So if the universal key is definitely universal key is a composite identifier. So we need to take part of each part of the key and then find out which columns in the universal is associated with the part of this particular key. Okay. So once you identify that, we can create a new entity with all the dependencies, right? So remove all these dependencies with this universal key, partial universal key or part key into a new entity. So likewise, you can um, remove the part key dependencies. Once you have done that, now you are in second normal form. Step 4 is we need to remove non-key dependencies. Do any attributes have functional dependency with a column that is not part of the universal key? If you have, you can create a new relation with the determinant and the dependence, right? So once you have created that, you are in the third normal form. So I have an example here. I have given a universal key or universal relation. Now you need to go through this table and try to normalize this table and come up with normalize database for this particular example. I have given the answer in the next slide. So please do it by yourselves by going through the steps that I have described and try to find out the answer for this scenario. So this actually ends the lecture 10.